So I'm going to talk today about software development methodology for RISC-V devices. Actually, I'm not going to be too specific about RISC-V. I'll talk more general about where embedded software methodology is going. But I do want to reiterate my position, which some of you have heard now for the third time, that software is really critical here. And in fact, the size of the RISC-V market share, I believe, will depend more upon the software ecosystem than on the specifics of the RISC-V implementations. So what I want to talk about today, agenda-wise, I'm going to go through some of the challenges in embedded software development. I'll talk about a new methodology, continuous integration and continuous test, a little bit about testing with hardware, and then the adoption of continuous test. And then I'll run through a worked example and then summary. So the embedded software development challenges, I think pretty much those first ones everybody is familiar with on the software side, schedule, quality, security, safety certifications. But what often gets lost on the software side are management issues as well. So the predictability of the software engineering task, the management accuracy on the software resources needed and on the schedule requirements is plus or minus 50%, roughly. Maybe it's a little bit better than that today, but actually if you were to, well, most of you are on the hardware side, if you start an SoC development project right now, management knows probably plus or minus 10% how long it's going to take and what resources are required. So there's a definite issue there with the engineering discipline side of software development. And also on the management side, there is an unknown and unmeasurable risk in the software that you're delivering. How do you know where you are on that? So those are the challenges. Well, let's talk about now how the software methodology is evolving. So software development pretty much goes by this V-shaped path, starting from initial concept all the way to deployment. But actually, that path, that V-shaped path for software development, is not the current methodology that's being used. Modern software development is moving away from this to agile, continuous integration, and DevOps. And this is essentially what that looks like. Some people will just call agile sort of that left side of the drawing there. Some people call agile the whole methodology. Using DevOps for the right side. Let's see, I've heard agile upstream for the left side and downstream for the right side. But there are a couple of points to this. One is that this isn't the V-shaped methodology anymore. The second thing is that by looking at the different areas, the development, the coding side on the left, continuous integration in the middle, and the release and deploy on the right, you actually don't have to jump into agile with both feet. You don't have to do everything at once. You can actually choose an area where you want to jump in. For this talk, what we're going to do is focus on the continuous integration piece of the agile methodology. So again, not going to talk about jumping in with everything. So motivation for the change and benefits of continuous integration. One of these benefits is better code structure and quality. With continuous integration, the whole idea here is that on a regular basis, the software engineers are checking in code, and when they check in code, it automatically builds. And when it automatically builds, it automatically gets tested. So this frequent code check-in pushes developers to create more modular, less complex code. It also enforces a discipline of frequent automated testing, which is a good thing from a software perspective. And then in this methodology, there are also software metrics that are generated from using tools in addition to just doing the testing. So tools for code coverage, code complexity, feature completeness, And so this helps focus the developers, the metrics help focus the developers on developing functional quality code, and they also help develop momentum in the team. These metrics also help software management, obviously. There's easier debug when unit tests fail or bug emerges. If you need to revert the code base back, you've been doing regular check-ins. It's a lot easier to go back. There are fewer major integration bugs because you're getting immediate feedback on the system-wide impact of local changes. The integration bugs are detected earlier, and if you've gone through a release process where there are lots of last-minute check-ins, then actually this helps avoid that. And then the last thing is that there's always a current build available for testing, for demo, or even for release to a customer. You need to get a release off the head to fix a bug for a specific customer. So, what are some of the problems with implementing continuous integration, continuous test? One is that there are multiple code streams that you need to manage. You've got development code, you've got code under test, code in the field. You've got many hardware and OS targets. You've got different processor variants because you may be shipping your device on different, maybe shipping your code on different devices. You could have code running on different versions of Linux, different versions of Windows, common code between the targets with many teams, many tasks, actually all going in parallel. So how do you all get this coordinated and running? There's also access and configuration of available hardware. Most people do testing on hardware right now, software development on hardware. We have a customer, the U.S. Air Force, actually, maybe a little bit extreme, but most of their hardware is actually up in the air and flying, and they can't do software development on it. They've got one prototype for a specific system that we've been working on, and it takes 2 weeks for an engineer to get any reasonable amount of time on that actual hardware prototype. This brings back memories for those of us in the room of old computers and card decks and timeshares, and it's an ugly sort of thing. So this is also not just about testing that something works, but ensuring what you think is being tested actually gets tested. And then running literally thousands of tests on many targets to validate the software changes. And with the common libraries and the different processors, you need to revalidate on all the projects. So automation can address this. Continuous integration, continuous test. Starting with continuous integration, you create a build server that so that any change builds the software for the multiple code streams, for the multiple targets. And then with continuous test, you run n number of test cases, could be thousands. Actually, we use this internally, and our standard test base is somewhere around 12,000 tests, which run in about 8 minutes for each of our developers. So you run n test cases, you quantify the correctness, you get coverage metrics, you actually get performance metrics out of this as well. So again, what we're looking at here is going from the developer to the compile, build, and test part of this, continuous integration, continuous test. So moving on to the testing itself, how to do this testing. You can use an x86 PC native. In other words, you can compile your embedded code to x86 and run that. This works well for fairly simple code. For example, in the automotive industry, running on x86 has been standard procedure for a long time. But now, as the automotive industry is moving towards more complex software, multi-core devices using more complex operating systems, using AutoSAR and things like that, running on x86 doesn't work. There isn't actually, as far as I'm aware, an AutoSAR port for x86. So if you're going to do actual testing, you've got to run on the actual device, or you need to run on a simulation of that. And then you've also got different things with binary libraries, with CPU architectures with restrictions. So for embedded, real target code should be used. By real target code, we mean code that is compiled for the target, that uses the correct binary libraries, uses the correct instruction streams. So you need to run on the real CPU architecture, you need to run with real data, you need to run with real stimulus, capture real outputs. So those are the requirements. And now how to do that. Because using real hardware is actually a problem. You need the device under test and the environment, both available in hardware. You need to stimulate the environment. You need to have sensors. You need to have buttons. You need to monitor responses and measure the correctness, both in value and in time. And the hardware may require manual intervention, which is prone to errors. How do you go and test a GUI? It's a little bit tough. Or in the automotive area, the human-machine interface, the HMI. Can a hardware test bench do everything you need? Does it give you the controllability, the visibility? Can hardware be set into the correct state to start a test sequence? The thing is, it can be hard to model the real world and hard to make it reproducible. And then there are more issues. There's how much access can you get for your testing? Can you have several users using this in parallel? Prototypes are costly to acquire and maintain, and they can only run in real time. So one of the things with some of our customers working with microcontrollers, so for example, this customer Audi, they're running on a nightly basis something like 6 months of road test data as their stimuli for simulations. And if they had to do that on the real hardware, it wouldn't run fast enough. In this case, the simulation runs probably about 3 to 4 times faster than real time. It lets them run more tests on a daily or nightly basis. So we would say here, and the trend we see in the industry is that adopting continuous test for embedded systems needs simulation. So imagine a software build system without access to make around. They enable effective build automation. What simulation does then is to enable the effective automation of testing embedded systems as part of a continuous integration and continuous test environment. So simulation enables full automation with no manual intervention. The use of hardware is just too hard. So virtual platforms, simulation, software simulation, enable CI/CD for embedded. What we're talking about here in terms of virtual platforms are instruction-accurate models, instruction-accurate simulation. So the virtual platform-based methodology delivers the controllability, visibility, repeatability, automation, and access. And actually what we found from working with our customers and what our competitors in the virtual platform business found is that 75 to 90% of the bugs are functional bugs and can be found using instruction-accurate simulation. We're not advocating getting rid of hardware testing. Actually, testing of timing-sensitive software and final testing still needs to be done on the actual hardware. But whatever your software stack is, you can run it on the hardware or on the virtual platforms. These are complementary technologies. It's not one or the other. So what are we talking about here in terms of simulation? We can look at this in terms of just the instruction set simulator, just a small thing for the CPU, or a full virtual platform or virtual prototype, which includes CPUs, memories, peripherals, test components, stimulus generation, models of the actual world or environment, and also software verification and validation tools. If we're just talking about an ISS, then what we're looking at here is just selecting a CPU model like a RISC-V, running the application, typically an ELF file. It's going to get run on the simulator. There are environment files. You can actually bring in using file I/O. You can bring in your test stimulus, you can output to those, and you can connect the debugger to that, whether it's GDB or a third-party debugger, whatever you're going to do. Pretty simple to do all that from ISS. You can get more complicated than that if you're looking at a full SoC, or even more than that. So what the virtual platform is a set of instruction-accurate models that reflect the hardware on which the software will execute. This could be a single SoC, it could be multiple SoCs, a board or a system. It's a virtual platform. There's no actual limitation to it. So essentially, the software should not know that it is not running on the hardware. So again, it's running the executables compiled for the target hardware. It's using the same tool chain that you would use for your hardware, but now it's running in a simulation. These models are typically written in C or System C. The models for the individual components, like an interrupt controller, UART, Ethernet, are connected just like in the hardware. These peripheral components can be connected to the real world. So you could actually use Ethernet and go out through the host PC Ethernet and onto the internet. And typically we're seeing 200 to 500 million instructions per second as the performance for this. Or if we're looking at something like a quad-core ARM being simulated here, the simulation will boot Linux in somewhere around 10 seconds. As far as the architecture goes, there are three components. There's the virtual platform models itself, there's the simulation engine, and there are tools. For comparison purposes, if you're thinking about QEMU, an open source ISS, QEMU is pretty much just the simulation engine and the virtual platform models. What QEMU does not have is the tools that we show over on the right. These are things like tracing, not just instruction tracing, function tracing, OS tracing, profiling, code coverage, scheduler analysis, memory monitoring, protocol checking. There's a whole suite of tools that are needed here. So the simulation is a key component, I would say an enabling component of the embedded system CI/CD environment. What I wanted to spend a couple of minutes on here is just what this looks like. And I'll talk about our internal environment, because we use CI/CD internally, as I said. We use the Jenkins open source tools for this. Jenkins is a widely used open source CI/CD environment for general software. So mostly there are actually trade shows and conferences for continuous integration, and the Jenkins tools are there. And most of the companies that are there do website testing or mobile app testing or things like that with CI/CD. And it's now being moved into the embedded world. So the idea here with Jenkins is to go through your software edits, to compile, local test, and check-in. Doing this check-in triggers the build. Successful build then triggers the testing. Testing completion triggers results, and the results get sent out to the appropriate developers. So Jenkins has a number of items. I'm not going to spend a lot of time on what the screenshots are here, but in this example that we're running through, this is a JPEG encoder, which is targeting 4 different ISAs, ARM, MIPS, Renaissance, and Altera, with 11 different algorithm arguments to test. So you've got a fairly limited test space here, but it's representative of the sort of things that happen in embedded systems companies. So these individual items, those line items in the previous screenshot, can use make to go and build. These scripts like bash to do testing. Then they run through this various stages. I'm not going to spend time on the details of this. But the final stage is to then collate the results. There are some graphical outputs from Jenkins, and you can see the results at the end. And it lets you see how the tests perform over each run. Management gets a dashboard. This is actually very good from both an engineering and a engineering management perspective. Of course, with the dashboard, you can drill down to see the failures. So what we're talking about here in this demo is a simple example of developing and testing code for embedded targets using cross-compilers to build, and then just a simple ISS to execute. This uses Jenkins. It's actually pretty simple to set up and manage. We have our own internal system that we had developed over a number of years. Actually, switching to Jenkins took us about 3 weeks of work. So it's not that much to actually go and do. This automates building and testing, and I showed this here for an ISS, but this extends to full virtual platforms without any trouble at all. So since I'm up here and I've hopefully got your attention, a couple of minutes on Imper and what we're doing with RISC-V. So we've got a website called Open Virtual Platforms. On Open Virtual Platforms, we have a library of more than 170 high-performance processor models. We've got pretty much all the embedded cores there, and recently we added the RISC-V cores, both 32 and 64-bit cores. We've also got on the Open Virtual Platforms website a peripheral model library and platforms. These models are open source. They need a simulator to run. There's a reference simulator, OVP-Sim, that's available on the website. And you can just register on the OVP website, download a free evaluation, and get going on this. The key technology here is the development, debug, and test tools. So I talked about the difference between QEMU and what we have in the environment, but just to add a little bit more clarity to this, one, these tools are non-intrusive, so we're doing things in the simulator and not in the code. So, for example, if you were using G-code for code coverage, you'd be instrumenting your source code, and that can change your results. With the simulation, there's no instrumentation, there's no modification of the source code. Also, these APIs that we use for building tools are available to users to build your own tools. The idea is to have tools at the appropriate level of abstraction and granularity. So if you're thinking about porting Linux and bringing up Linux on your device, Linux is, to get to the boot prompt, somewhere around 1 billion instructions. So looking at an instruction trace is a difficult thing. But if you've got OS-aware tools, then actually there are only about a little over 700 tasks when you boot Linux. And so it makes it a much better starting point for doing your debug. I've got a couple of examples here. I mentioned Audi before. I won't go into too much detail, but what they're doing is building a tire pressure sensor that's an algorithm that runs on multiple processors. Testing is very important for these guys. Another customer of ours is a company called Nagravision. They build devices that protect streaming video. The interesting thing here, these guys use continuous integration methodology. But their key quote here is that software simulation is mandatory to reach the metrics that are required for their high-quality, secure products. We build solutions for custom and proprietary processor modeling, for pre-silicon software development, software test, and also power and timing estimation. And then just to summarize what we've got, some key technologies here. Processor model library, including RISC-V, a large peripheral model library, very fast simulator, and the tools to go with that. Solutions for embedded use cases, and the way software methodology is going. experience with continuous integration and continuous test usage. That's what I've got. Thank you very much for your attention.
I have a question regarding, because I'm an embedded developer, so sometimes we'll run into the problem that might not come from it might come from the fuses or the boot code, or that part of the code in the SoC is not open to us. But I guess if you implement this virtual simulator, you might get access to the boot code, at least to logic. So is there any way that this Imper's toolchain can help with that, or maybe that's a part of that? Only we can get help from the supplier and boot code.
So there are some things that that can be done there. One is, depending upon what issues you're having with the boot code, sometimes it's illegal memory accesses, and so it's easy to put together memory monitors that are non-intrusive. Another thing that we've done with another customer is actually to work with their software suppliers so that we can build some specific tools that essentially things like assertion checkers that can be in the simulation environment, so that you still don't have access to the code, but you have test points with the assertion checker to show you where things are going wrong, which can provide a test case or provide feedback to the software supplier. So there are things that you can do that give you more visibility into what's going on than you would have when testing on hardware.
So with the help of the supplier.
Yeah.
Thank you.
CI/CD is a cool idea, and I'm a user of the GitLab and the Jenkins users, and I'm very glad to see talk about these things here. Two questions. One, a lot of the test case, they will different report, like LTP, GCC test case in it, or GDB, they have the DAG framework. So there were so many test report come out. How do you analyze them? Question one.
Okay.
Or you just build it and let the user to analyze them. Okay. This is question one. And question two is you have visualize the platform simulator, and I see the picture. You have found analyze the PC trees. So once you implement it for the QEMU, grab all the PC trees out and analyze by your own tools or applications.
I'm not sure I understand the last question. This is a tool that is completely separate from QEMU. So we've built our own models, our own simulator engine, has nothing to do with QEMU at all. All I'm doing, because I think a lot of people are familiar with QEMU, is just comparing what the Imper's environment looks like to what QEMU does. On the first question, that's really up to the individual company. I've seen a number of different things. The way we use it internally is that when each user checks in their code, we run those 14,000 tests or so. That runs in under 10 minutes, so that the user himself can get immediate feedback on that, and they can go and solve their own bugs. But there's also a roll-up that we do when we do a larger integration, and then engineering management takes a look at the bug reports, and then usually we get together and talk about how those are going to be fixed, because some of the integration bugs. It's unclear at the beginning where it may have been caused by something implemented by one designer, but maybe it needs to be fixed in another piece of code because of the way the code is evolving. So it's just depends on the individual companies.